Welcome and good evening to you all. It's a pleasure tonight to introduce Paul Gannon, who's many of you will be familiar with his Rock Trails book, the series that he's written on walking geology for walkers and hill walkers in the UK. So it's a pleasure to have Paul present tonight. He's presented a few in the past on the Lake District and on the mountains of Britain as well. So it's great to have him along tonight. The talk will last about 50 minutes or so. We'll have a break halfway through, and those of you who are familiar with my presentations, I normally do a kind of interactive Kahoot. So if you have a second device, a phone or something, if you'd like to play along with the Kahoot, then it's just a short 5-question quiz, a bit of fun during it. And then at the end, I'll have an opportunity to field any of your questions. So if you've got any questions during this presentation, just put them in the chat. I'll deal with any technical issues in the background. If you've got any questions, we'll field them at the end. And we'll also do a bit of a hot debrief, a hot feedback. Some of you are familiar with another interactive app called Mentimeter. So we'll do that right at the end. And a good, exciting day for me. I've had my latest educational product launched today. So I'll share that with you at the end as well. So for now, I will hand over to Paul, who's going to share his screen and enjoy.
Hello everybody, welcome to this talk on the geology of the Peak District. I hope everybody can see, not me, but a picture of the lake, of the Peak District with a nice green colour on the hills. And if you can all see that, I'm going to get started. The core of the Peak District, all the rocks were essentially laid down in the Carboniferous Period, which is one of the divisions of time that we use in geology to organise our understanding of the past. So all I have to do is get this thing up. It worked. So we're going to look at the Carboniferous Period, which ran from 359 to 299 million years ago. So let's say 360 to 300 million years ago. And the Carboniferous means carbo is Latin for coal and ferro is bearing. So the rocks of the Carboniferous Period are coal bearing. They aren't all coal, but they do have coal seams within them. And we'll go into a little bit more detail of the types of rock as we go through the talk. So what I have to do is work out how to switch slides. So if we take a look at the geological time column, on the left here, we have divisions going way back beyond 550 million years, the Precambrian, followed by the Cambrian, the Ordovician, the Silurian, and the Devonian. In the Precambrian, Cambrian, Ordovician, and Silurian, rocks in the Peak District area were laid down that became the basement rocks on which the rocks of the Carboniferous Period were laid down. During the Devonian, no rocks were deposited in the Pennines at all, the Peak District or the Pennines at all. After the Carboniferous Period, in the Permian and the Triassic, and also the post-Triassic, which I've just lumped everything together beyond 205 million years ago, some rocks were deposited, but nearly all of them were later eroded away. So there's very, very little of these left in the Peak District. We'll explode, looking more detail at the Carboniferous here. And we have three main subdivisions. The Carboniferous limestone, mainly limestone, and some shale, and also a few volcanic rocks in the Peak District, such as in Cavedale, for example, and one or two other places. Then we have the Millstone grit, the youngest. They are younger than the Carboniferous limestone, sit on top of it, mainly shales and sandstones or grits, with some marine bands in recursions by the sea with fossils, And then we have the coal measures, which are a very minor part of the Peak District, but we will chat about them because it's a story that sticks together quite well. Mainly shale, but with thin seams of coal. Incidentally, there are also some very, very thin seams of coal in the Millstone Grit as well. I have a book from the 1950s on coal, and this diagram's a bit busy, but you can see all this hatching, diagonal hatching from upper left to lower right. The author reckon that all of this would have been continent during the Carboniferous period. And the reason for that is that coal-bearing coal is found Australia. I've lost my pointer again. I don't know. Sorry about that. I've lost my pointer. So anyway, they reckon that the continent must have been much bigger than it was today, because we had so much of the coal in North America, in Britain, in Europe, South Africa, South America, Australia, India, and so on. So therefore the solution was to say, well, the continent must have been much bigger than it is today. But in fact, we know nowadays, of course, that this is not true. The continents are bigger today. They've accumulated over the years. And of course, the explanation is that about 350 million years ago, all the continents were joined together in a single supercontinent, Pangaea, rather than being spread out. And this explains why we get the coal measures appearing all over the different continents today. They were all created at the same time, roughly around here in the center of the Pangaea, and then all the continents are broken up and spread out, and so we have all these Carboniferous coal-bearing layers spread all around the world. Another fact that's a quite interesting, important fact about this time actually goes back to the Devonian, but in the Devonian we developed the first trees, proper trees. And then there were lots more trees in the Carboniferous, especially during the period of the coal measures. And so what we're having is the creation of the continents for the first time becoming green with these photosynthetic vegetation, which was letting out oxygen into the atmosphere. If we take a look at the next slide, we can see an example of a very early tree, a lepidodendron, which was about 40 meters tall. And these trees grew, they developed a substance called lignin, which allowed the trunks to grow, strong trunks to grow and have tall trees. But the microbiological life forms, which would normally break things down when the trees died, hadn't developed at that time. So we got more oxygen into the atmosphere than was broken down by decay as the trees collapsed to the ground and they weren't broken down. The carbonization didn't take place and carbon was sequestered into the trees or the plant life on the ground. And we can see this here in this little diagram where we have got, in the bottom diagram, we've got the level of oxygen. We've got this great boost in oxygen up to about 35%, whereas today it's about 21%. And on the top part of the diagram, we can see the rise and rise of the giant insects, which followed very closely on this increase in oxygen. It allowed the insects to become much more substantial in size. So that the giant dragonfly-like insect shown on the left had a wingspan of 75 centimeters, and the creepy crawly on the right, the Pulmonoscorpius, the scorpion, had reached a length of 70 centimeters. So it was it might not have been a very nice time to live despite having green plants. We didn't have to cope with these wild massive insects. So there are important differences between then and now, but it was an important stage in the development of the Earth. And it comes back to this issue of the carbon cycle, whereby a carbon was sequestered in the dead plants and they didn't break down, and they went on then to form limestones, shales and coal, which I mentioned earlier on, were key parts of the Peak District geology. So let's have a look at some of the basic plate tectonic situation mentioned earlier on. We had all the continents that joined into one, and we have a, sorry, it's very annoying, but I can't find my pointer. I don't know what's going on there. Sorry about that. Oh, here it's come back. We have land mass off to the right here, Europe, with this high land, the Wales Brabant High. In the background, you can see modern day England and Wales shown, but of course that wasn't there at the time. And then we can take a look at a cross section from south on the right, going up to the north through that same Wales Brabant High over here on the right. And what we've got is that an extensional tectonic environment. In other words, the plate is pulling apart and it's allowing these deep fault lines to occur, which we can see in the central high. And the limestone, which is the blue, is dropping down below sea level. Whereas in the white peak of the Peak District, we've got the limestone at surface level. In the dark peak, we've got the millstone grit at the surface level. And then higher, further north, we've got in the Ingleborough, Malham area, we've got limestone at the surface again. So we have a look at the geology map from above, the white peak, the limestone plateau so-called, which is surrounded on three sides by the millstone grit rocks. We have a look at a closer view of present day. So initially we had this extensional, this pulling apart of the plate. Then the late Carboniferous, it was a compression that was taking place, squeezed the rocks inwards, and our limestone, as we can see, formed this gentle anticline, an upward fold. Whereas the softer millstone grits, shales, they were formed, as you can see on the far left, into closer folds with smaller anticlines, syncline, and further anticline. And in the middle, in the Goyt Valley, the Gold Sitch area, we get the coal measures sitting in the syncline as well. And then we've got this major fault separating on the left, on the western side, separating the millstone grit from the Carboniferous limestone. On the east, we've got more millstone grit, but they are broken off. And there was millstone grit joining the two extremes, the west and the east, but it's been eroded away. So this is our present geology. So we'll have a look at, if I can get the thing to move. It might have been Jim letting somebody in. Apparently I lose control of the screen when somebody's being admitted. So we have a look at a little bit closer at the White Peak. On the left, we've got a map of the whole of the White Peak, a very rough map with our Carboniferous limestone. On the right, we've got a cross section looking from south to north again. And what we've got is the limestone, the shelf or carbonate platform limestone, forming a platform up to 2,000 meters thick as the limestone is created in warm, shallow seas. And we've got two things going to happen which allow this limestone to develop so thickly, because it's created close to sea level, surface level, because you need the warm sea for the limestone to create. As the limestone builds up layer upon layer on top of itself, it is depressing the rocks below, the mantle below are depressed, which allows the top of the limestone to remain just below sea level and for more and more layers to be built up. And we also got, as you can see, on the extreme outside, we've got apron reefs and some knoll reefs, which we'll talk about in a moment. These build up, and you can see on the map our apron reefs occur roughly round the edges of the limestone carbonate platform, and the knoll reefs more central to it. So we can see a photograph here of the edge of the White Peak limestone carbonate platform here in Castleton area. This is Winnats, and it dips down into the Millstone Grit shales over here. The White Peak is, sorry, jumped on one too quickly. A White Peak is really a green peak, and we do actually only really see the limestone outcrops in a number of places. The best places to see the outcrops actually are the quarries where it's been exposed, and also some of the gorges that we have, but the limestone gorges, which we'll talk about later on. But you can see the limestone here is building up in these layer upon layer, built up on top, and this is highly fossiliferous rock, fossil-bearing rock, as we will see in a moment. And this is a knoll reef. We were talking about the reefs as well. And this is an apron reef, and you can see this is quite a high. We've got very little bedding indication here. We've got what's known as massive effect rather than the bedding stuff, and you can see the height from the scale from the person at the bottom of it. And these reefs are a limestone mud, which is very tiny particles which are formed by either chemical precipitation, disaggregation, or the falling apart of small pellets of carbonate of limestone, or a process known as microtization, which is where algae, fungi, and bacteria ingest the limestone, the calcium carbonate, and then excrete it in tiny fragments, which are then cemented together to form these reefs. So they ingest the skeletons of the living creatures which have calcium carbonate skeletons. Just that remind us of the overall view. One thing that's misleading about this diagram, in the limestone, the Carboniferous limestone, it looks as if the layers of limestone from the swatch, which I've used in the background, are horizontal, but in fact they really should be curved like the anticline that we can see. And if you start off, for example, in a Manifold Trail walk and follow it through from near Buxton outwards, then you at the nearest to Buxton, the bedding is dipping down to the left, and over here, further to the east, it's dipping down to the right. So we have actually got this anticline. One of the places you can see it is by following the Manifold Trail. However, in some of the edge parts of the limestone, the folding is more smaller in scale, such as here at Apes Tor. And you can see, if I can get my pointer, we've got a syncline here, and then there's another anticline there, a small scale syncline in rather shaly limestone. So it's mixed in with a lot of shaly material, not the pure limestone that we see in the central parts. I'd look at some of the features of the Carboniferous limestone. And one of the interesting things about the limestone is that mechanically it is a very strong rock. So it forms, as we'll see later on, forms some upright walls in the gorges and so on, and here in the dry valley at Cavedale. But it has a weakness in that it is dissolved in a mild acidic solution. and the water, rainwater and soil water that is slightly acidic, will dissolve the limestone, sink into the limestone, and it will then form its own structures. And so we get sinkholes, such as this one in the middle of the White Peak, where water sinks down into the limestone. We can have more impressive looking sinkholes, such as here, Cell Gill sinkhole. This one is a cavern, which will be an underground cavern where the water would drain away. This one's quite close to the surface, and there's later, newer caverns below which now take the water out, whereas this cavern is open to view from above. And then we get the opposite of the sinkholes, we get springs, so that when it's wet weather, there will be a stream coming out of this hole here, out of the cavern and into the valley. And of course, the other famous feature we get in limestone is the pavement, the limestone pavement. Actually, what happens is that limestone, because it dissolves, doesn't leave material to create a soil. So the soil is created only by material that is blown in and captured in place. And most of it now, the limestone pavement of the Peak District is covered, and we only get small patches of it, such as this here in the Dove Valley. Further north around Ingleborough, there's some amazing stretches of limestone pavement, and also some fantastic ones. This one is from the Burren on the west coast of Ireland, with this massive sinkhole, dolly as they call them, in the centre of the photograph. And we also then in the limestone, we find vast number of fossils and vast type of fossils. Here we've got marine shell fossils. We've got a feature of fossils of crinoids. These are very common. We get these circular lumps which stick together, form part of the crinoid, and here we can see some of the lumps that have been split into apart, and we've got a small circular shape. This one here is about 1.5 centimetres, 2 centimetres across, and the crinoids are actually an animal. They aren't plants. They're called sea lilies, which is slightly misleading, but they are plants. They're called sea lilies because they tend to look a bit plant-like. And so these columns anchor them to the floor, and then they have a mouth ingestion point around here in the middle, and then these arms which wave food material in towards the mouth. And you'll find all over the place crinoid fragments, and occasionally if you're extremely fortunate, you might find one like this, which is actually taken in a museum, not out in the field. And then we have another interesting type of fossil. Might not look much like any other fossil you've seen. It might look like shells, but in fact it's what's known as a stromatolite. And these are calcium deposits formed by cyanobacteria, and they're layered sedimentary formations. They're photosynthetic, they supply oxygen to the atmosphere, and they form these microbial mats, one layer at a time, building up on top of one another. And they can be seen in different places around the Lake District as well, stromatolites. So these are plants, not animals, and the crinoids are animals, not plants. Okay, with that, Jim, I'm going to take a break while you do your quiz.
Thank you, Paul.
Take a loo break. You've got a couple of minutes to do so.
No, don't go for a loo break. Play the Kahoot. Paul, could you just stop sharing for a second? And for those of you who are not sure of Kahoot, I'll just, hopefully you've now got that pinkish screen with Kahoot, and on a phone, if you were just open a web browser and type in on a web browser kahoot.it, then it will ask you to put a game pin in. I tried this with Paul yesterday, so we trialed it out. I got Paul using Kahoot yesterday. It will ask you for a pin and then have provide a name. So it's a bit of fun. If you can't do it, don't worry. You'll still be able to quiz yourself with the questions. So the game pin is coming up now. 7250282. And then I'll ask you to put your name in. So I can take 50 people on this. So I've had more before, but I think they only allow 50. So while we're doing that, Paul, there were 3 or 4 questions. So we'll be able to answer those at the end.
Yeah.
Okay. I think people can join in a bit later, but I will just start for now with the people who have joined in. Peak performance. 5 questions, multiple choice. Meganura is the largest known flying insect alive in the Carboniferous, but how big was its wingspan? Paul did give the answer to that earlier, so yeah, well done. Just over 2 feet. So well done. Well done, Mike, there. For the quicker you answer, the more points you get as well. So. Pulmoniscorpius is a breeding scorpion and the world's largest arachnid. But how long did it grow? And it was 70, yeah, Paul gave the answer to that earlier on as well. So well done there. So Ed, well done, just jumped into the lead. The Peak District is famous for its mineral-bearing rocks, but minerals form in which rock type? Calcite, and Paul will maybe be able to explain that a little bit later on. Well done, Ed. The semi-precious mineral mined in the peaks is a form of fluorite with purple-blue colouring.
So what's it called?
Called Blue John.
Right.
And there's a Blue John cave, isn't there, in
Castleton, yeah.
Castleton, yeah. So well done, Ed. Again, the final question. The Peak District was first designated national park in the UK. True or false? Yes, it was true. So just have a quick look at the podium. Well done, Liz. Sharon, 5 out of 5, fantastic. Good effort, Ed, thank you. There we go. I will stop my sharing there and Paul can share his.
I've got you. Share. Have you got anybody got me on the screen?
I can see it, Paul. So if anyone can't see it, then just drop it in the chat.
So you should all have a delta accretion slide on,
yes,
on your computer now.
Yeah.
So we went through the formation of the various types of limestone and some of the features you can find in them. Then you may remember at the beginning pointed out after the limestone we have the millstone grit. What we've got is a different environment in which the rocks are being laid down, or the sediments being carried down to make the rocks. And what we have got is a delta. This image shows the Mississippi Delta today. And what you have is the flow from the river, low level into the sea, and our earliest flood event was number 7, which was about 4.6 million years ago. Sorry, 4,600 years ago. Number 6 was the second flood event. Number 5, the third. Number 4, number 2, 3, 2, and then number 1 is the most recent flood event that we've had in the Mississippi. And so this would be a very similar situation when the Millstone Grit was being laid down, where you get a flood event for some reason or other. Material flows out over the sides of the river drainage columns, and basically it separates itself into roughly 2 types of sediment. The heavier sediments drop out the quickest and form the sandstones, and the smaller sediments, the mud, stays in solution longer, drops out of solution much more slowly, and forms our shales. So we get this mixture of sandstone and shale formed by these flood events in our delta. And we get the formation of the dark peak. And we have, you can see here, this very layered look, whereas where we've got a steeper slope, we've got our sandstone, which is resistant to being eroded away. Then we have the shale, where the flat parts are, being less strong, less tough, and is eroded away to form the flatter parts. So again, we have the situation where we've got the tough parts forming these Millstone Grit edges with shales down below further. And what we have, for example, in the center of the photograph, we have big, solid, tough sandstone. And then below it, between 2 layers of sandstone, we've got shale, which is much softer and is eroded away more easily. Eventually, of course, what will happen is that this will collapse down. And this is what the millstone would look like if we didn't have all the vegetation collecting, forming on the sides. This is Millstone Grit quarry. So this is a classic Millstone Grit. And we can see loads of it are on the areas of the Millstone Grit, but we don't see shale very much because it's eroded away and covered by vegetation much more. Features we see in the Millstone Grit, very common in the Peak District, is the bedding, as one layer after another layer is laid down in this swamp environment. Or feature here known as cross bedding. We've got some bedding here at this angle, slightly tilted. There's been a shift of the current, which shifts where the currents are laid down, the beds are laid down, sorry, and we can see them horizontal here, or more or less horizontal, cutting across the lower beds. So we get this feature known as cross bedding. These are quite common features in the Peak District. So we've just got the same diagram again, just to remind us of the situation. We've got our Millstone Grit being laid down on the edges. We're forming the sharp edges, Stanage edge and so on. But where we've got this down as well, we've got the coal measures forming in this syncline. And we would have these flooded delta lobes. In the above picture, we've got an unflooded situation, and in the lower one we can see the floods have covered a lot more ground. And then when we look at this diagram, the upper part we've got a collection of dense vegetation on the slightly higher sections, the levees or the barriers, and then we've got this more vegetation growing away from that point. Then when we get the flood, all that vegetational material collects on the floors of the swamp. It doesn't decay away, and slowly forms into peat, and then on into form coal as well. So we don't get a lot of it in the Peak District, but there is a small amount, and it is part of the story. Our shale, as I said, is weak. So here's an example where it can be seen on the surface. We've got our layers of shale here, layers of shale over here, and a collapse because it's so weak in the middle. And this is in the Gold Sitch area. The next two photos, this one and the next one, aren't from the Peak District. They are from South Wales, but they are heavy-fingered. Sorry, I have to go back. They are plant fossils. They're parts of trees, whether they are branches and the leaves would have been attached in these holes, or they may be roots, parts of the root system. But as I say, I've never seen any of these in the Peak District. I've seen plenty in South Wales. We'll come back to this diagram, which reminds us this side point that we have our weak shale, which is eroded very easily, and our tougher sandstone. And this leads to a quite common feature in the Peak District, which is the landslip. There are indeed hundreds of landslips in the Peak District, and they are basically caused by the weak shale crumbling away, collapsing underneath the stronger sandstone, which slides down in rotational measures and forms then this classic hummocky landscape. This is the way you really can spot them all over the place, is by the hummocky landscape. Here in the Bretton Clough, here on Lord's Seat and Rush Up Edge, again we've got the hummocky landscape which you can see has slid down the side of the hill. And the most famous, of course, of all is Mantor, much more substantial. Most of the other ones that we just looked at, they were landslips about 8,000 years ago, well after the end of the Ice Age, and the frozen ground had ceased being frozen, and the collapses started occurring. But the landslip at Mantor is somewhat younger. It's about 4,000 years ago that it took place. And what we reason is we have this situation where on Mantor itself, as we'll see in a moment, we've got a layer after layer of sandstone interlaid with the weak shale. And then at the base, we've got very massive amount of very weak shale, the Edale shale. And during the compression, where we saw the anticlines and synclines were made, that Edale shale was so weak that it was all effectively transformed into a mush. And that is what is falling apart below the sandstones on Mantor itself, which is also known as sometimes a shivering mountain because it's continually sending off lumps which come crashing downwards. This is, if you've not realised, it is a map of the different phases of the landslip, from the rock face backscarp on Mantor over here, the slide zone in the middle where the slide transforms into a flow, and then this still advancing flow zone, which they reckon will continue to flow for another 4,000 years before it reaches its furthest point and settles down and doesn't move anymore. And there's a photo then. Looking from the top of Mantor, we've got a classic situation that you see in a landslip or landslide. This is curved or arcuate slip backscar here. Classic thing to look for. And looking in Mantor, we've got all these layer after layer of sandstone interlaid with our weaker shale. Another example of it. And then this is the road, which was built in about 1810, and for 100 years they attempted again and again to repair the road but it was placed on top of the Edale Shale, which, as I said, was the weakest part of the whole structure, and was continually, literally flowing away. And here you can see the road flowing down. Here you can see the white line still in the middle of the road. Further flow of the road down here. So in 1979, they stopped trying to maintain the road, and it's now a walkway. It's quite interesting to walk down from the top to the bottom. And then one further photo. This is actually the tip of the advancing flow. It's quite difficult to get in. It's a bit a squeeze through all the vegetation to get there. But you can see it is moving forward and pushing over these trees that were upright, like these trees which are growing in the flow. These ones were growing outside of the flow and are being pushed over. And then just down on the right, down here, a little bit out of the picture, there's actually a farmhouse where the flow is approaching that farmhouse. Whether they'll manage to be able to divert it around the sides or in the end have to give in and accept the fact that the landslide is going to engulf the entire farmhouse is yet to be seen. As it will take a few hundred years, we're afraid we will not find out the answer to that question, probably. So one other feature which we ought to mention about the Peak District, which is very common, are the fantastic limestone gorges. And we have a funny situation. For example, this is Dove, part of Lower Dovedale, and the River Dove flows from north to south roughly, and it cuts through the middle of limestone hills. It comes up to a limestone hill and cuts through the middle of it, rather than going around the side of it. And how did this happen? Well, if the answer to that question goes back again to that picture we had of the anticline forming in the middle. That anticline is forming through slow pressure. It's slowly building up, becoming a higher anticline. But the river manages to keep up and cut down into the gorge, into the mountain, forming a gorge faster than it's being pushed upwards. So we have what's known as superimposed drainage feature on the hills here. This is very common in the Peak District, where a lot of this happens, not just in the River Dove, but the River Dove is a classic example. And we come back to the point that these limestone in these gorges is mechanically very strong, often forms vertical walls, or here in the Wye Valley, we can see we've actually got overhanging side walls, indicating the physical strength, the mechanical strength of the limestone, despite the way that it can be dissolved by water. And I think that is 7:45, finished just on time. Just a little advert for the Rock Trails series. We've got Rock Trails Peak District, other areas, and then we've written with Jim, who did the flower sections of The Alps, A Natural Companion, which came out last year. And you can get these books from Cotswold, Joe Brown's, good bookshops, cheapest of all on Amazon. Most expensive of all, I'm afraid, you can buy them from my books, my website. It's the way the economics of the book industry work. I can't offer them too cheaply, but you get a signed copy for the expensive price. So with that, I say thank you very much. We've had a rush through the geology of the Peak District, looked at the rocks, the environments in which the rocks were laid down, and some of the main features that we see in the Peak District. And with that, I'll hand back to Jim and we'll deal with the questions. So I think I stop sharing now.
If you want to, yeah, that's fine, Paul. Thank you very much. Very, very interesting run through there. A couple of questions came in, and please keep them flowing if you've got any questions now. Alistair said something quite early on. Why were there no rocks laid down in the Devonian era?
Because at that point, the land, the surface of the upper surface of the rocks would have been above sea level.
Okay, so
For
there's no
sedimentary rocks to be laid down, they've got to be below sea level. If they're above sea level, they will be carried further down into the sea somewhere else. Or you need something like volcanoes, but we haven't got volcanoes to lay down the rocks. The land, the surface, the top surface of the rocks would have been above sea level, so no rocks were laid down. So we don't have old red, typical rock of the Devonian is the old red sandstone, which we see, for example, South Wales, adjacent to the limestone. And we don't see that in the Peak District. I hope that makes sense.
Yeah, people are nodding. I can see that. That's good. Ross Weston put a link in the chat as well for a PDF. So if you can hit that and download that, a walk along the Manifold Trail from Hulman End, and you can see the layer on the side. And that's to do with the limestone that we saw earlier on. So it's a good example of where to see that feature. Next question from Anne Clark. How is, you talked about limestone pavement and the soil, but I don't know if you answered it before the question came out, but if you could just repeat about the formation of limestone pavement.
Right, well, limestone, imagine at the end of the Ice Age, it's a good starting point, all the rocks would have been bare, all the material, all the vegetation on the rocks would have been scraped away by the glaciers. So when the ice melts, all the rocks would be bare. And soil forms partly from the breakdown of the rocks by vegetation. It creates matter which forms soil, and some of the other material will be blown in by the wind. But because our limestone is dissolved away, it doesn't leave material to form a soil. So in the limestone areas, the theory is that it must all have been blown in where there is soil today.
Thank you for that.
Oh, that makes sense.
Yeah. Question from Adam Clark. Why is it that gritstone has a harder outer layer and a softer, more erodible interior?
It doesn't have a softer interior. The interior is the shale. So if we go back to our flooding events in the delta, as I say, what you're having is sediments brought down by a river and deposited when they hit the sea. When you have a flood, you've got a mix of sediments. Larger sediments are sand-sized sediments. All these definitions, sandstone, sand, mudstone, depend on the size of the fragments. So sandstone is near enough visible with the naked eye from all sandstone, all sand. And they're heavier, so they will settle out of solution in the water more rapidly than the mud fragments, which are held in solution and will settle much more slowly. So you get both types of sediment being brought down by the flood, but the sand forms into sandstone more rapidly than the mud forms into mudstone. Then you have another set of floods, and it's repeated again. So between the tough sandstones, you're going to get a weaker rock type, the shale, which is a mudstone, which is the finer particles. They're more easily eroded away.
Great. So thanks, Paul. Although I was thinking on a micro scale, where, say, climbing gear erodes the surface of a crack away and exposes a lighter sandy texture, which is easily damaged. So he was thinking more on the micro scale for a climber's perspective.
Right. Well, what's happening there is that in the sandstones in the Peak District, the sand is cemented together. Part of the process of forming the rock, lithification, is this formation of a cement that holds the rocks together. And then when they're exposed to the atmosphere, chemical changes start to take place which break down that cement, and that releases the sand fragments. And you can see this if, for example, if you walk around, I can't remember the name of the place. Gone from my mind completely. You walk around an area where at the top of, near Castleton, what's it called, where the waterfall is?
Cavedale? No, not on that.
No, the other side, above the Edale Shales.
Holland's Cross?
Kinder Scout, sorry, Kinder Scout. How can I forget that name? You walk around Kinder Scout, you'll see that the paths are very sandy. And that's because the sand has been exposed, been released from the rock by erosion of the cement that holds the sandstone together. Does that make sense?
I'm sure we'll get a nod or something from him.
Some nodding I can see, yeah, on the top row.
Chris Muscat, something we put in the Kahoot, but not so much in the presentation, was about the minerals. But Chris Muscat asked, why is Blue John unique to the peaks?
That I don't know. I don't know the answer to that one, I'm afraid.
No problem. Can you recommend any good books on the geology of Ireland?
Of Ireland?
If you can't think of it now, then we can have a chat and I can send it as an email to everyone later on.
Yes, and I'll add the Blue John as well. I'll try and find out the answer to
that. Someone's asked if you could produce a geological map of the UK for their hostel in the Brecons. I think the British Geological Society have downloadable maps or purchasable maps as well, don't they?
Well, I seem to get quite a lot come up on Facebook now, of ones that you can put on your wall, which look quite good. I must get one.
Well, if that's it for the questions, what I've got now is I'm going to have, I'll do a quick screen share.
There is one question about BMC map of the Brecons. So the Harvey map of the Brecon Beacons will have a geology map on the reverse side. So if you get the Harvey map, then you will get a geology map of the Brecon Beacons area. Are you still there? Do I need to push a button for you, Jim?
No, that's fine, Paul. David Dobson's just said the blue-yellow colour of Blue John is related to incorporation of organic matter into the fluorite. Just by Treac Cliff Cavern, there's a small deposit of oil which has seeped into the fluorite.
Oh, right.
Thank you very much, David, for that.
There's a bit near there, isn't there?
Yeah. This is a part of a series. You should see the screen that I shared there. It's part of an autumn series that I'm running. Future webinars coming up in the next 3 Thursdays. I'll be talking about Britain's glacial heritage next Thursday. Paul will return to talk about the geology of the Alps the following Thursday, and then John Roberts, an upland archaeologist, will talk about archaeology in the mountains on the 3rd of December. I run workshops and Paul runs workshops, so they're recognised as professional development for outdoor qualifications. And I run a series of mountain environment, glaciation and alpine flower workshops. We can keep in touch via Nature's Work on Facebook or through my website. And this is a product that has just arrived today in lots and lots of boxes. So I'm going to have a giveaway. So you don't have to do anything on the giveaway except give me your address if you're the lucky winner. So I've entered all of your names into this wheel, I'm going to give 2 packs of these Trees of Europe cards away. So the first winner Andrew Pennell, you are a winner. Well done. I'll remove you, and it's gone a little bit slow. I'll do one more spin, give another way. I need your postal address. Ooh, looks like it's Neil Raha. So well done to the both of you. They are available through my website. So if you weren't the winner and you were keen to have a set of outdoor learning cards, playing cards, and I've got a series of them as well on flowers. That's my general theme, but the trees are really useful in the winter for identification. With a review and feedback, I don't know if you have a phone and you'd like to just share your thoughts. Again, if you use a web browser and type in www.menti.com, there is a code that you will be asked to enter, and that code tonight is 2996487. And there's 3 slides, and if you could just, the code is at the top of that screen that I'm just sharing there. And you can do it now, or you can do it later on, but if you wanted to, that would be really handy. It's great to just get instant feedback. Fantastic as always, educational, well paced, well judged. Thank you. Paul Rocks, there you go, Paul. Informative, concise, true grit. Thank you for your comments. They'll be coming in. Then we look at how we rate the webinar, various aspects there. So thank you for your feedback. I'll just have a quick look. Any of these comments or any of your comments that come in that are worthy of sharing with everyone, I'll send you all an email at the end of this webinar later on this evening. So if there's anything that comes up, then I'll share any comments. Excellent webinar, thank you. So yeah, thank you all for attending. I'll just minimize that, but yeah, there we go. It's almost 7 o'clock. So yeah, thank you all again, and I hope you have a fantastic evening, and hopefully see you again. Okay, bye-bye for now.